Hello ladies and gentlemen, my name is Jan. I build stuff so you don't have to. In case you didn't know, this is the Minuteman machine. It's an experimental 3D printer that weighs 1.3 tons and is packed to the brim with technologies that explore the absolute limits of physics in terms of 3D printing. The ultimate goal is to 3D print a Benchy in less than a minute, and during the last episodes we did testing with experimental cooling method. There was liquid nitrogen, dry ice included, we blew water vapor onto the print, we blew just water droplets onto the print and tested all sorts of different geometries and flow rates, you name it. And for some, this may seem like we are not doing any progress because there are no videos titled, hey, it's the next world record or something. But trust me, I think I have a very solid plan in mind on how we achieve these kinds of goals eventually. But let's not get ahead of ourselves. We need one last piece to the puzzle. This is filament. During the last episodes you saw me fooling around with this black PLA material. Then we switched over to some high-speed filament by Fiberlogy, more on that later, and had some great improvements over there. This is the Benchy you've probably seen in the intro with a thermal camera. Not too shabby for 3 minutes 20, but today we're going to take it a step further. I wanted to get around this for a lot of time because today we're going to do some testing, and I guess this will probably involve a lot of problems with bed adhesion and warping, you name it, but... Okay, welcome to my seating position here. Let me get you updated. So in terms of the machine, I did reassemble everything in here with our last test being a huge mess. I cleaned everything to the bone, lapped all the surfaces again, cleaned all the air channels inside, etc. And then if you have a closer look here, I did this as a test and this worked out quite well. I applied one of those BuildTech PEI sheets. These are very thin, a few tenths of a millimeter, and with a very thin layer of this glue stick, this seems to be helping pretty good for printing PLA on cold surfaces. First layer adhesion was pretty good. And as you can see, I've put in the Jason duct in here again. This has been working quite well, let's say somewhere in the range of 80% of my attempt on the cooling duct, but I will put a short clip in here why this is bad for our current testing. With this in here, I have no idea how to shoot good video out of that. So I opted with the Jason approach. As I said, this is working quite well and we'll leave that on here for comparability's sake. In terms of the prints, I already showed this shortly for a 3 minutes 24 Benchy. This is looking pretty nice. As you can see, overhangs are pretty crisp for that speed. Outer wall appearance is pretty dope actually. I haven't seen it that good. That may be because everything is reassembled good. As you can see, I had some very small shims in here, and also I experimented with coating all the surfaces, the glass on the bottom side as well as the granite, with some PTFE spray. And that seems to be helping quite a lot with friction. So my very outdated input shaper profile seems to be a very good fit for that. The second print I've made beforehand is I modified my speed tower again. For those that haven't seen that, it starts at 100 millimeters a second right here at the bottom, and then in 15 increments it works its way up to 1500 millimeters per second printing speed. And this is my scale to it. And as you can see, with this kind of filament and layer times, this is 6 seconds at the bottom and 0.5 seconds at the top. We managed to print all the way to 1400 millimeters a second, which is quite impressive. And have a look at the surfaces generated here, all the way from, let's say, 5 to 600. Below that you can see some artifact, but then again, this printer has never been designed to run 3-digit speed values. So everything here above 500-600 is looking pretty damn fine. Have a look here at first layer. So if this thing, and I will put a short clip here. If this thing doesn't come fly off, well, bed adhesion is okay. So what we're going to do next, we're going to go over the line of filaments I have lined up here. And we're going to try to conduct these both tests to put it in perspective. And yeah, filament testing, if done properly, takes a huge amount of time to get everything dialed in, because let's face it, there are no values I could pick from any kind of database that I just plug in here and that will work. So basically I will do as with my normal methodology, I'll do ballpark areas. So we kind of want to throw a material in. We're going to run the same code for all of these since we're not using any retraction values or something. We do have a pressure advance value that kind of works for PLA, but I don't want to like dial in all the filaments at the same time. I'm going to be sitting here for weeks. What I'm more interested in is ballpark areas and big picture stuff. So with a new filament being put in the machine, let's find out which is the lowest temperature setting we can reach our estimated flow rate, which is around 150 cubes for this kind of print. We're going to set it at that and just try to do a print. So with bed adhesion being a problem with PLA for kind of some time, I do expect to have a lot of problems with ABS and such. But I think we're going to start with ABS. Let's have a look over there. So this is the lineup, and you can see now why I did switch to this filament, because we try to take a lot of things out of the equation. So now we're running all these filaments with the same pigmented colors in there. And here we got some ABS in blue. This is ASA. I'm not fully decided yet if we're going to try this. Let me down in the comments if I should be testing ASA. I think for now we're not going to do that. And then I got some PETG also from the same lineup. This is stuff in the burgundy color. I think we're going to skip most of that because it's also PETG and ABS. This is something we're going to try the very last. This is some mystery material for now. If it works, I'm going to show you what it is. And in this box here basically is my joker for the very last test. But I'm also not going to say what it is right now. All this filament has been sponsored by Fiberlogy from Poland. They have been helping out for this project in the last couple of episodes as well. So a huge thanks to Fiberlogy and especially Dominic over there, who has been doing a lot of communication with me. Thank you so much for the opportunity to have a real test that is comparable. I mean, I could go on Amazon and buy 50 whatever filaments and the results would differ a lot. But this is manufactured on the same machines with the same tolerances, with the same pigments, etc. I can have a very clean swipe across all the filaments, and just the raw material has been changed throughout this test. So let me put the ABS on the machine and let us see if we can print anything with it. Alright, so this is the filament. Manufacturer says somewhere in the range of 250 to 265 degrees. I've heated up the hot end to 250. We're going to do filament swap. There is the ABS. Okay, and now what I'm going to do is, as I said, we have to deliver 150 cubic millimeters per second of volumetric flow. And I'm going to see if we can hit that number on 250 degrees. And if we do, I'm going to keep lowering the temperature until it starts skipping at that speed. So yeah, we can just deliver. You heard the clicks there. That was the first skipped steps. I stayed at 250, and at 250 it can deliver 150 cubes per second, pretty much. In the real application it's going to be lower. 150 is the max flow we're going to need. With the pauses in there, we're okay with that. But what we can see is how this extrusion looks after leaving the nozzle. First of all, I think it's pretty swollen up. This is still 0.4mm nozzle. This looks to be a lot bigger. So we're gonna keep increasing the temperature a bit. Let's do 260, see if we can get that ripple out of there. This is at 275. And as you can see, it gets smoother. What we're going to do with this filament and all the others coming up, you will be accompanying me on the very first print, just to see my first and initial reaction with the problem. Let's see if it sticks, let's see what it does. We're going to start by printing the speed tower. Then I'm going to take some time without the camera, try to dial it in as fast as possible, going a bit up and down with the temperatures, seeing what I can do in terms of bed adhesion, etc. And then we're going to follow up with whatever I came up with parameter-wise and show the final result of these two prints. So let us do that. Here goes nothing. This is Build-Tech PEI sheet with a very low amount of glue stick on top. I do have a fan running over here just to get rid of the fumes. And we're at 100 millimeters per second printing speed. ABS does need a lot less cooling, so when we reach a few hundred millimeters a second, I'm gonna switch it on lightly, just to get a ballpark idea. Okay, truth be told, I wasn't expecting that it would survive first layer. Up to this point there were no cooling effects other than the fan blowing a very low amount of air across the whole table. Then you can see we made it somewhere in the range of 800 before it started to go downhill. Interestingly, here in the front it is still okayish at 12 to 1300. So this cooling duct is pretty symmetrical and pretty well aligned, but it is obvious that it might have something to do with pressure advance or something. So it starts here, has some problems extruding that, but also you can see the curve in here. So a linear approach on a different pressure advance value wouldn't do the trick. Then it settles in at some point, and right at the end of the extrusion move it is pretty stable. So what I'm going to do is I rerun this at 260, 270, maybe 280 or something. Let me just see what the next ones look like. Maybe we go down in numbers. And I'm going to come back to you once I have all this. Alright, I got some results to share. First of all, layer adhesion doesn't seem to be that big of a thing. I felt like being catapulted right back into 2015. I mixed up some slurry from the extruded filament with the acetone and just put it mildly on here, and this was working quite fine. This is the one at 250 you saw. I bumped it up to 260, it was already looking better. 270 was even better. Here I learned that I have to reapply the acetone mix with each print. 280 then again started to look a bit worse. So with the last one I dialed it back to 270. And all of these are done at half a bar of cooling pressure on the duct. This one is at 1 bar of cooling pressure. This is going all the way up to 1500 millimeters a second and doesn't look too bad. Here, starting from let's say 1100 or something like that, it starts to get a bit wobbly, but this may also be because it's wobbling or rocking on the plate. I found the parameters to start with. Let's go 270 let's go 95% on the extrusion multiplier and let's freaking print a Benchy. I already set up the thermal camera, see what is happening there. You see, bad adhesion, bueno. Layer adhesion, we have to work on that. Yeah, but there you go. Let me get rid of those little stringings to compare apples to apples. I did that as well to the PLA print. Alright, let's talk about ABS for a second. This is pretty much apples to apples comparison. This is PLA, this is ABS, both printed around 3 minutes 20. Keep in mind with the same code. So the code is pretty old essentially. For a few months I've been using the same reference profile. Nothing has changed, nothing is optimized, and now ABS also has to take a go with it. So as you can see, this does show a lot of potential if you see over these little boogers. This is something you clearly can do with temperature settings, with pressure advance, you name it. What you can see is that the cooling performance is better on the ABS one, because this one is pretty much cranked up all the way to 2 bars of pressure. This is 1 bar. And that is why all these overhangs here at the tops do look a bit crisper, because there is not that much downforce pushing that filament out of the way. As I said, 3 minutes 20. I then printed this guy here. This is a 2 minute 30 Benchy. So basically 25% speed override more on that, without changing code, etc. You can see that we're on the limits of cooling, but it was also 1 bar. Then I printed the same 2 minute 30 Benchy with 2 bars of pressure. So what I wanted to know is, does it scale with the amount of cooling we put there? And the answer is a complete yes. If you have a look at this overhang here, 1 bar to 2 bars, that is definitely an improvement, as well as the overhangs here on top and the chimney. So what this tells me is that all the things we did find out earlier on about adding water vapor or cooling down or cooling media will apply to the ABS. So I think this shows a lot of potential, but as you can see, I have already unloaded the filament because this will do just fine for now. I got my results, ballpark area which I want to have. Let's put on the other filaments. Let's see if this shows the highest potential of them all. If it does so, then we'll get back, develop a very own slice just for that material, and yeah, go from there and just have that dialed in. We'll continue in a second with our content and testing the PET-G, but just a quick word from our today's video sponsor, which is again PCB Way. The thing so often is that hobbyists and makers do want to build stuff, create ideas that are stuck in their head. but it is a problem if you don't have access to a lathe, to a mill, to a laser cutter, to you name it. So basically PCBWay offers a website where you can just upload your parts in various formats and get an instant quote on all different processes like CNC milling up to 5 axes, sheet metal stuff, 3D printing in basically all the materials you can name, and also of course PCB manufacturing. So there is a link somewhere down in the video description. You can follow that and get a small discount on your first order there. I can highly recommend their service. It takes basically seconds to get an instant quote on all the parts you want to have, and then it's just a matter of day until you have them in your hands. You should totally check that out. Thank you again PCBWay for sponsoring this content. Let's get on with PETG. As I said, PETG is loaded. This is the filament code if you want to follow that to the Fibology website. I had to bump this up to 250 degrees to get the required flow of 150 cubes. And that goes to show how insanely good their high-speed PLA actually is, because this is also rated at 220 to 250 just as the PETG, but I can run almost 300 cubic millimeters at sub 200 degrees. So if you're in search for a really high flowing material in PLA, this is some pretty good stuff. Now, as I said, temperature is being set in for our very first test. We're going to start with the speed tower again, and for the very first print I'm going to take you with me on the tour. Since this is already on, I applied the last bit of acetone goo I had on here. I figured it won't dissolve the first layer just as it does with the ABS. But since there is some kind of plastic deposited here, maybe this will make up for a pretty good printing surface. At least check that. If not, I have a lot of these slugs over from the Build-Tech material. Then we can find something else to print on. Let's just see how that goes. Let me try to peel that off first by just... Jesus Christ. That is sticking like crazy. Interesting first print. It finished all the way to the top. And again, extrusion starts going this direction, so we clearly do have something with pressure advance and stuff like that, but the rest of it does look pretty good actually. So same thing, I think we are low on temperature. This is 250, let me do 260. Well, you know the deal from ABS. I will report once I have some parameters found. Whoop whoop. So that did work out pretty good. As you can see, 250, 60, 70, 80, and lastly 275. All of these are done at half a bar. This is 1 bar. My initial thought was, oh, I'm gonna be having bed adhesion problems, but bed adhesion is actually so good that on all of these parts the bottom surface ripped away, and it got increasingly more, so my prediction is that I'm wearing off the acetone layer. The last one I pretty much had to chisel from the plate, but it cleaned up pretty good, and now I just put on a very thin film of glue stick as a separation layer. I'm in no way affiliated, but this Build-Tech thing does work very properly, as well as the Easy PETG. It pretty much stands up to its name. It just does work at all the temperatures. I mean, it's rated from 220 to 250. Pretty early on I noticed that I need more temperature to get the flow up there. And then you can see with the first ones, it Does take some time until extrusion like settles in and then works quite good. The more temperature I gave it, the more that gap became closed until it was almost closed, but then you can see, especially on the back side, we have some wobbliness, I think due to insufficient cooling. Then on the last one I dialed it back a few degrees and gave it 1 bar of cooling, and this is looking pretty good. So now I want you guys to shout it with me. Benchy, Benchy, Benchy. So this is the first 3D-Benchy I've printed. Overall, some very decent spots, 275 on the nozzle and half a bar of cooling pressure. As you can see up here, we run into severe limits of physics. The next one is with 1 bar of cooling, same temperature, so that has made some serious progress in terms of that overhang up there. And then the last one. And then on the last one, I just pulled out 10 degrees out of that nozzle heater, because I was noticing that down here we don't need too much flow and it's working pretty alright. But here we can't get rid of the heat. And 10 degrees less up there seemed to be helping again. And still, this is the same PLA code, so we can compare the three we got. This is PLA, this is PETG, this is ABS. And then last thing I did, this is the ABS Benchy 2 minutes 30, and this is a PETG Benchy 2 minutes 30. You can see what 30-40 seconds of printing time does make of a difference. And that's why I'm always telling you guys in the comments that it isn't really making any sense to build a profile for a 6, 7, 8 minute Benchy or something. You have to dial everything in for that very spot you want to print in terms of times. You can't put any parameters from a data sheet on here. It's going to be such a huge difference if we're printing 600 or 800k accelerations or 1500 millimeters a second or 1200. So yeah, we have to dial that in on the spot. I think both filaments so far did show a lot of potential. Right now I'm leaning towards the ABS, but now comes the real fun part. Because you were always pointing out that we should use some kind of a filled material that gives it better conductivity or something, because the next one will be a filled PETG. But I'm not gonna disclose for now what it is filled with. I think this is task for tomorrow, which in your case it's gonna be now. So I want to point out two things. So first of all, I have a Discord server. You should totally check that out. There is a lot more information available than you can see on these videos, because I keep on posting there while I'm doing this on the machine. Also, I'm having a Patreon, and I did my first cash out there, and this is basically what enabled me to fund this thermal camera that is recording behind me. And I want to say something to all of you guys. You know the deal by now. Filament is already loaded in. As I said, filled PET-G material. It's only available in black. Yeah, for comparison's sake, it is like it is. Everything is set up. You know the deal by now. I'm gonna take you on a tour on the very first print with it. Let's see how that goes. This is being untouched from yesterday since PET-G worked flawless on it. Again, Buildtech PEI coated sheet with a thin layer of glue stick on top. This is the standard PET-G. This was at 280, and these seem to be about comparable in terms of extrusion quality, but this is 40 degrees lower, and this is kind of what I was hoping to see here. No problems at all reaching 1500 millimeters a second at only half a bar of cooling pressure. So same as here, I'm gonna go up and down a bit, see where we find our sweet spot, and I'm gonna show you the result. So this is a peek at the few specimen of benchies I've printed, and this is the material. So this is by Graphene, the PET-G Strong. This is been 5% fill with graphene flakes. Graphene, you ask yourself, isn't that the material that has been discovered in the 1900s as a concept and then further developed and ultimately rewarded with a Nobel Prize in 2010 for their researchers in Nijmegen in the Netherlands? Yes, it is. This super material, it's a 2D atomic structure of carbon atoms, and if you can manage to not have a three-dimensional state of it, just have it purely oriented in a 2D pattern, then these carbon atoms form something that can only be described as a supermaterial. All the parameters in terms of strength, conductivity, basically you name it, are off the charts. And basically to this day it is a problem of production. Well, I thought it would be, but apparently there is a company somewhere, I think it's also Poland, that has developed this into a product for 3D printing, and it's also dirt cheap, which surprised me a lot. I was thinking a lot about filled filaments for this test, but I want to give you an example why I'm not using carbon fiber or something with copper or metal fillings, all that stuff, because this hot end has been running like a trooper. But I fear that as soon as I put abrasive material in here, I will get into trouble, and if I ever have to maintain this thing, I'm going to rebuild it completely, and then it will be down for 1 week of work. So that's why I am going with non-abrasive filaments, and according to the website, this is non-abrasive, so I can print it with a brass nozzle and all my self-plated nickel inside the hot end. The theory and why I was so hyped to test this filament, they claim that it's a 170% increase in melting performance over a natural PET-G. Does make sense because there is a lot more conductivity inside the filament. But we don't have the problem with melting. As I said many times before, we're running at 20-30% of the melting capacity of this hot end for the 3-minute benches we're doing here. But cooling is what interests me, and this is basically the same principle. So for the very first, we started out basically from here to here. This is half a bar of cooling pressure and 225 degrees. This is also 225. Forget about that. Then I got down to 215 and even did one with 208, but this was too cold. Went back to 2015 and cranked up the cooling to 1 bar. Then I had some issues with bad adhesion, and this is kind of my finished product for now. I haven't done anything to it, so please use your imagination what it would look like without all those boogers and those small defects here in the outer wall. Since I had the experience with the Fiberlogy PETG, I didn't think it was necessary to do the speed towers as well. It was pretty obvious that it would be 1500 doing easily, and I went straight into doing some really crude brute force attempt to get a Benchy dialed in-ish. Obviously it's still running PLA code. Nothing is optimized for that situation, but it's showing a lot of potential for sure. But let's not get ahead of ourselves. The next video, as I mentioned probably in the beginning, will be about dialing a Benchy in sub 2 minutes. We're not gonna do that here. We're gonna continue with filament testing. And now we're gonna do something which you probably have never seen before. Since my hot end is really one of a kind, we can do something I haven't seen on the internet. I want to do a co-extrusion test. And the list of parameters that we could throw at this machine and possible benches is huge. And it has been a problem from day one to sort of like get in the ballpark area for all of these. I'm going to introduce a new variable, and that is to combine 2 filaments together. In a very early episode where I built the first initial hot end, I had colors mixed in there, and I noticed that basically lane 1 and 4 basically wrap around lane 2 and 3. What I want to try now is at least have a very crude look at how we can improve filament furthermore to make it for our very specific use case. And I was debating with myself yesterday if I should do it or not, but since I can extrude this at 215 degrees, I can match this with PLA. And after a bit back and forth, I decided to have PLA as a core and the PETG with the graphene on the outside. I don't want to get started why I choose this specific configuration. You can put everything down in the comments what we should combine together and why, of course. But this is the best temperature match I have here. For now, I can't run independent temperatures on these lanes, but now we have some fair grounds and also different colors, which makes it kind of visible what is happening inside the filament. I will put this in, hopefully not screw up my hot end in the attempt. And then we're going to print some co-extruded material and just have a peek at it. I don't want to get somewhere dialing this in or something. I'm probably just going to go hit print at 215 degrees. I'm going to take you on the tour and we'll just see what happens. I thought that would look different, but here we go. Extruding at a 150 cubes. But just as a proof. So let me grab a specimen, let's put it under the microscope, but I guess with this nozzle size we won't see shit, but I don't know. Let's have a look. Alright, there you have it. It's black filament, right? Until I turn it. So as you can see, the wraparound isn't perfect, but there is a PLA core inside. Let's just freaking print with it. Yeah, so this is what came out of here in comparison to the PETG graphene alone. And for anyone doubting that this is a co-extruded filament, there you can see it. That layer adhesion may become the issue here was as expected. PLA and PETG usually don't bond with each other very well. I've used that principle here a number of times as a support material, but then again, this seems to be quite solid. It detached here. You can also have a look inside. The PLA is nowhere to be seen. Obviously, this isn't like the thing I'm after. But what you can see is what kind of potential we have in this technology. And somehow with this test I want to spark your creativity down in the comment sections. Basically we can build our own filament now. Composite materials, combining the best from all filaments. Right now my mixing or co-extrusion isn't perfect because the hot end isn't designed to do that. I've just found that out when I was doing multicolor tests a few episodes back. But you can see that despite being 50% of that here is being bluish, this is pretty much a black print, so the whole wrapping around part is basically working for 80–90%. And there is a lot of viscosity things going on, so basically if we choose the lower viscosity to the outside material, the wrapping around will be better. So build a strong core, build something on the outside that has very good layer adhesion and also gets rid of heat quickly and solidifies fast. Go down in the comments and tell me what I should be put into this hot end here. Okay, that's it for this test. I've done enough just to spark your creativity here. Let's do the last filament I have on the bench for today. So the point why I am using this as a very last test is because the chances are pretty high that I'm gonna mess my hot end up with it. But I will take the chance at least for a test ride, since this machine will be undergoing serious reconstruction anyway. Now it's the time to test it. So this is, and of course this is not the perfect setup, but this is PCL filament. Polycaprolactam, whatever, you can read it here. And this is primarily used in 3D printing pens. The main property why it is so interesting is this has a printing temperature around, it is listed in the datasheet from 70 to 100 degrees. And the glass transition temperature should be around 40 to 50. So what that means is that our delta we have to bridge from having a puddle to a more or less solid state is around 30 degrees or something. So we have to do very little cooling to it. At least in theory. This is the only thing I could acquire without breaking the bank. This is pretty cheap stuff. The rest of it is primarily used in medical applications with biocertificate, etc. So what it is basically designed to do is you print something, you heat it in a bucket of water or vapor steam it or whatever to 50–60 degrees, and then you can mold it around certain parts to make it a perfect fit. These filaments are quite costly, and also they do have additives in there that list the extruding temperature from 130 to 150, which defeats the purpose of this. I can basically extrude PLA at that temperature. I can put 4 spools together to make a test run, basically just extrude some filament if I make it this far, and then I have 3 attempts more. Each of these spools should be worth a few benchies. But foreshadowing if I make it that far. Because problem is, and I've been thinking about that for quite some time, how should I get rid of the leftover material in the hot end? Because this is now filled to a certain degree with PLA and PETG. What I did is I heated this up to 270 for quite some time, have gravity extrude most of the material out, at least I hope it does. And now I have set it to 180, which is basically the lowest temperature I think I can extrude PETG and PLA out of this hot end if I'm doing it very slowly.
So yeah, basically almost instantly the second lane did skip steps. This probably means that it's being pushed up there through the heat break and solidified there. Strangely, it's always lane number 2 that makes up problems, but now since I do have that thermal camera, I can't really find any issues here.
I just wanted to report that after 30 minutes of fiddling around, I got lane 2 unstuck. Have a peek who's here. So the hot end is set to a 100 degrees. I'm gonna do a very short extrusion move. I know, the second half of the filament guide is not installed here. So I'll install this again, see how far I have to push up temperatures to get at least a considerable amount of flow. And if this is nowhere near, I'm gonna step back, because now I got the chance to get away with it without having any damage to the hot end. If it's not worth trying, I don't want to spend a few days doing maintenance. Okay, I finally got it back in working order. Just for good measure, for a good clean, let's run some PLA through it, 240 degrees, 350 cubic millimeters a second. So I guess it's time to wrap this video up. Have a look at how much more experience we got with these tests. So these are old, everything down here, the bench is new. And I think this helped us out big time on the long-term goal of eventually printing a Benchy in less than a minute. I mean, when I say it right now, we're still far away. And as you can see, with all of these filaments and a bespoke machine just to do it, we run into the same walls of physics each and every time. But let us have a closer look. I am fairly impressed with all of these materials. I was kind of scared running anything else besides PLA, because we all know how predictable and easy to use it is. As I said many times, in engineering, it is a valuable thing to take a step back and reconsider everything you know for a fact. I thought it would be an absolute nightmare to print ABS and PETG on the system, but it did work out quite well. I mean, essentially, I had better layer adhesion than with a PLA before. In terms of the graphene material, it actually shows us how much additives or filled materials can help us with finding the right parameters for printing. And as I said before, we unfortunately in the current configuration we can't run all of them. Copper-filled filament will be highly abrasive, as well as anything related to carbon fiber. I mean, I could do that at some point where I will do maintenance anyway, and wearing this thing out in a matter of a few hours doesn't bother me. But I'm not there yet. The next episode will be me trying to tackle a sub 2 minute quality Benchy. All the things you saw there, these are all 3 minutes 20, and by the way, all the thermal footage you saw is always 3 minutes 20 to make it comparable to each other. We have to be a lot faster than that, and claiming to be able to do a sub 2 minute quality run is a bit of harsh, so I don't do that. As I said, I will try to do that. But I do have fair grounds with all the research we've done over the last couple of weeks and months to have a solid plan to do that. And cooling is still the main issue here. So we can combine everything we've learned so far and apply it to a whole new set of filaments. So the question now is, what would you do? Which filament would you choose to carry on with our quest here? Since there is the basic possibility of combining stuff, the options are pretty much endless. I want you guys to put anything down in the comments or come on the Discord server. And to wrap this up, I have a few MVPs for this episode I want to point out and give a special thanks to. First and foremost, thank you PCBWay for sponsoring this video, making all of this somehow possible. Then to my Patreon subscribers that allowed me to buy new stuff as the thermal camera as shown in this video. Then of course, Fiberlogy for providing all of this material here. Just to make that clear, I didn't receive any money from them, just the material itself. But I would like to point out that the customer support was top-notch and all the products worked like they are intended to be. I didn't have any problems using them. All of the materials are like factory sealed, so I didn't worry too much about humidity. For future tests we will have them dried before usage. Then, thank you to Jason and Lewis for initially designing those two ducts that were used throughout this entire episode. It is not quite there in terms of performance compared to my setup, but it enabled me to do proper filming. Then, thank you to Nathan. Nathan did provide me with a tip on the PETG graphene material, and he's been designing and building a very special 3D printer, I think over there around the Prague area. And I'm just in awe with this design and how it works. So I'll put a very short video of the so-called Ston-Wolf 3D printer here.
I am quite persistent.
As well as a link somewhere down in the video description where you can find like his channel. Last but not least, again, I'm not affiliated, but the BuildTech PEI sheet was just working flawlessly for all these materials when being printed on cold. I would have never thought that would work in any way, but it did, and this turns out to be a very viable solution for the future. Last but not least, somehow thank myself, because this machine has been doing 40 back-to-back high-speed prints without ever skipping a beat. Not a single missed step, not a single whatsoever hiccup from the extruder hot end setup. Everything has just been working flawlessly. And of course, this is the result of a lot of work that has gone into there. But this is basically what you need to get comparable results in any way. So, I hope I don't jinx it with that. This is really the end of the video. Put everything you want to tell me down in the comments or on my Discord. My name is Jan. I build stuff, so you don't have to.